Okay, good afternoon, everybody. Let me introduce myself. My name is Patrick Gallot. I'm a software support engineer for Data Logics, and this is my introduction to color in PDF. Okay, just to give you a brief overview of what I'm going to talk about, for need eye candy for presentation on color, and I chose to use optical illusions for the eye candy. And so you're going to be seeing a little bit of color simulation, lateral inhibition, simultaneous contrast, and maybe after images. And after that, we're going to, well, that'll be throughout the session. To start off, we're going to have a bit of basic color theory, a very brief introduction to it. Then we're going to go slightly longer over the basics of PDF color. And then for the second half, we're going to go beyond the basics using some of the more advanced features using Edward Tufte's indicator of color use as a frame. Okay. First, we're going to start off with a quote from Joseph Albers, who in 1963 wrote a book called The Interaction of Color, and the illustration is actually one of the cover images that was used for one of the subsequent editions of the paperback version. It's actually the first illusion in a sense because it looks as if it's like a transparent sheet with this corner folded over a tiled background. In fact, that's an illusion because there is no transparency that was used to actually create this. It's 10 different geometric shapes, each of which has different color values. Okay. So to start off with the color theory, colors are basically a narrow band of the electromagnetic spectrum, just like AM/FM radio or television or Wi-Fi signal. But in that band, we can see certain colors, and each of those colors within that range is actually a distinct color. And we have warm colors at the low end of the frequency range, and we have cooler colors at the higher end of the frequency range. The warmer colors being your reds, yellows, and oranges, well, not in that order, and your cool colors being your greens and blues. Let's see. But it's basically our eyes that allow us to see color as things, and basically you have different cones in your eyes that perceive different colors, and by mixing the two, you have cones for, well, red and green and for blue, and by mixing primary colors that involve those colors, you can recreate most of the color spectrum just by mixing those colors. But the thing is, there is a genetic mutation that causes color deficiency, color blindness, where you can have people who do not see red, do not see green, or less commonly do not see blue. But there's also another mutation where women, in particular, have an extra cone so that they can see more reds than men usually. So the point of that is that perception of color is not uniform across everybody. Not everybody is going to see color the same way that you do, which is what makes it a bit of a challenge. Let's see, and then we talked about the spectrum. Besides the spectrum, you also perceive it by seeing the brightness, which is basically the intensity of the light that carries the color, and then the purity of the color, which is how washed out or pure it is. See, how does this relate to PDF? Well, actually, let's go a little bit to printing and paper, because since we're trying to mimic what goes on with paper with a PDF before we actually get to printing. When you start with, every device is going to have a unique color gamut, and a color gamut is basically the range of colors that it can reproduce. And it's not necessarily uniform where you can only do so much green, but some devices might do a little bit more green or a little bit less red or whatever. It's not necessarily a linear progression. Every color gamut is going to be unique for every device. Um, let's see. And generally, printers are going to have a smaller color gamut than displays. But ironically, color fidelity, I think, is going to be more important with printing than it is with color displays. Let's see. And with printing, the paper that you print on, we think of it as white, but it can be all sorts of white is not necessarily a unique color. And if your paper is off-white, that's going to affect the vividness of your final image, because not as much ink is going to bounce back from the paper. Well, not as much light is going to bounce back through the ink to your eyes. Let's see. And finally, which is why when you're doing professional printing, where there's actually money on the line for the printing, professional printers will use standard illuminance to see how exactly the print job actually looks under standardized lights that more or less conform to how it might look in other places, because color can look very different under different types of lights. So they might use typically D50 or D65, which is color temperature, lights for a certain color temperature, to check the print, but they might also use other standard illuminants, like incandescent light, to check, just to make sure that in the final environment that it's going to look the way they intend it to. Okay, so let's start with achromatic color, which is basically grayscale. Well, black and white and shades in between. And actually, when you talk about that in terms of printing, grayscale is a bit of an illusion itself, because you basically have the paper and you have the ink, and you're actually using halftone patterns to cover up a certain amount of the paper with ink so that it looks gray. And let's see. But there are also certain types of printers that will not just do halftones of black ink, they'll also do light gray ink, so that they can extend the range of the just the halftone patterns to make it more, there's more continuant gradients between from white to gray. And okay, many grays created by equal screen percentage. We'll talk about this a little bit more later, but let's get to some of the eye candy to begin with. Let's see. Question for you. Does the square in the center look darker than its surrounding? It actually, the color gray is uniform throughout. What makes it look as if it's darker is because there are black lines going through it, whereas the white lines outside of it. But it's actually a uniform gray background. The white lines, in a sense, act like a halftone pattern, where if you think of this were printed on paper, more of the white of the paper would be coming through, whereas in the square area, the black lines may get a higher density ink, so it's a bit of a halftone pattern there as well. Let's see, that's not quite the way it works with projected onto screen, but that's one way to think of it. So let's look at another illusion. Another question for you. Does the gray on the left, is it the same as the color of the bar on the right? Or is it different? Well, it's the same. But if you, well, usually what happens is that you pick up the color from what's around it. So by the darker color, it'll look lighter than if you look at the other end, where it's by the lighter color, it'll look darker than it is. But it's actually the color around it that's changing it. And I want to talk a little bit about how this particular illustration or optical illusion was created in PDF. It's basically three rectangles. The outer and the inner rectangles are both device gray, and they're the same color. But the rectangle in between it is in a different color space. And a color space, the best PDF has, I think, 14 of them. The best way to think of a color space is really that it's like if you think of feet, inches, centimeters, kilometers in physical values, they're basically the units. Color space is a unit for color values. And that's true for everything except the color space that I actually use for this, which is a pattern color space, specifically a axial shading pattern. And I'm going to basically with this one, I'm going from white on one end to black on the other end. And I'm actually going to reproduce this on my next slide with different ways of specifying white and different ways to, well, actually, white I'm basically keeping constant, but I'm going to different ways of specifying black. I like to call this next slide 15 shades of gray, even though I can't count, because it's actually 16. And I'm going to briefly talk about the ones that don't look so gray. The fourth one from the left is actually CalRGB. And the thing with that is that when I printed this on a PostScript printer, that it looks pinkish on screen, but when I printed it, it came out nicely uniformly gray with good color tone throughout. But when I printed it on our PCL printer, it came out pinkish as well. So it's you might as well worry. Most people don't use CalRGB these days anyway. To go to another 4 down, actually, can I? The one that looks like it's black throughout. And what I specified there is basically its device CMYK, or 4 color channels. Basically, it's register black, which means I'm going from white to 400% in coverage if it were actually being printed, which is something that you don't want to do because what you'd have is dot gain issues where there's so much ink on the paper that your ink would bleed over beyond where you intended it to go. And then to the next one that looks a little bit brown. One of the books I researched basically specified that you can have blacks with a warm tint or a cool tint, and they suggested certain values for a warm tint, basically 50%, well, 0% cyan, 50% magenta, 60% yellow, and then 100% black to give black a black tint. Well, that would probably only occur at the very top, and the rest of it looks like a bad shade of brown. Whoops. The next one, 2 down from it, is where it looks bluish. That's actually supposed to be blue, well, supposed to be a cool tint of black at the very top. So since these are specified as device CMYK, let's talk a little bit about subtractive color. Subtractive color, basically you're usually dealing with translucent inks, where you have light that basically shines through your ink, bounces off the paper, and then either is absorbed by the ink or comes back out. And what comes back out is what gives you your color. Let's see. There are basically, with the CMYK, mentioned cyan, magenta, yellow, and black. It's basically 3 primaries plus a 4th ink, black, which you can use to shade the color to make it darker. Let's see. And one thing about it is if you combine 2 of these primaries together, you get a semi-pure color. Or if you combine all 3, move that out. If you combine all 3 of them together, you get gray. Okay. But And what you do to lighten the color when you're printing is you use halftone patterns, which basically removes ink from the so that more white shows through, which lightens it. Okay, another illusion. This illusion actually uses, do you see bluish discs at the intersections of the lines? Okay. I don't personally see bluish discs at the center of the lines. What I tend to see if I look at this too long is I start to see diagonal lines between the cyan crossing. But this was created actually specifying device cyan in device CMYK space, and I'm actually using a line dash patterns for drawing the crosses. Moving on. So let's talk a little bit about additive color as a flip side of subtractive color. That's basically if CMYK or subtractive color is your natural color space for printing, RGB or additive color is your natural space for screens, where you've got light coming out from someplace and going directly to somebody's eyeballs. Let's see. Okay. One thing I want to point out, well, the primaries in RGB, most people know it's red, green, and blue. One thing I do want to point out with RGB is that your primary colors have secondary colors where you combine two inks together in equal amount. Those are actually the primaries for subtractive color, and vice versa, where you combine two of them together, you get the primary color for additive color. We'll see that a little bit more in the next screen. And then basically you get if you do equal primaries, then you get gray, and if you have enough gray, then you get, well, if you increase the intensity, you get white, as opposed to in subtractive color where you increase the ink, you get a darker color. Let's see. Enough of this, let's look at two color wheels, one for RGB on the left and CMYK on the right. Obviously, the CMYK on the right is a simulation of what would happen if you were printing. These two color wheels are actually created in the same way. Basically using gray code to change one color component at a time, starting with 12 o'clock at the top, red at 12 o'clock, and do want to say the inner wheel is actually, I'm using index colors for them, but the inner wheel I'm using fewer colors, and I'm doing, as I'm going out, I'm increasing the interpolation between the colors, going from the primary and secondary colors. Let's see, your primary colors are going to be at noon, and 4 o'clock and 8 o'clock. So red, green, blue, cyan, magenta, yellow on both sides. Your secondary colors are going to be at 8 o'clock, 10 o'clock, and 2 o'clock. And if you actually start from the top at noon, you can follow red, orange, yellow, then green, blue. Indigo is really a shade of blue, and then violet, and then back to red again. One thing about it is complementary colors are actually 180 degrees opposite of each other on the color wheel. So the complement of red would be cyan, and if you combine those two together, you get gray. If you're putting together a color palette, let's see, you can select colors which are complementary, or if you can do something that's called a split complementary, where the colors are 150 degrees apart. So if you look at 7 o'clock, 2 o'clock, and 5 o'clock, you can do a triadic selection where your colors are 60 degrees apart, so say 3 o'clock, 5 o'clock, and 7 o'clock. Or you can do an analogous selection where your colors are 30 degrees apart, so say 11 o'clock, 12 o'clock, and 1 o'clock. So let's go back to looking at a color illusion. Question is well, there's basically silver rectangles. Are you seeing a color gradient going from left to the right or right to the left? Or is it uniform? Okay. It's actually uniform. Actually, it's used device gray to do the silver in the middle. And what happens if you do see that it looks as if there's a different color, it's because it's picking up the color from the orange on the left hand. And as you go towards the right, you're getting more and more blue, so it looks cooler than it is on the left, where it looks warmer. Let's see. Let's look at another optical illusion. For this illusion, if you recall what I did for saying the complement, the complement of yellow, well, yellow is at 2 o'clock on the color wheel that I just showed you 2 slides ago. Its opposite would be blue, and if you go just to the left or to the right of it, you can have, that can cause pronounced simultaneous contrast, and simultaneous contrast happens a lot with pure and semi-pure colors. Thing is, they can cause simultaneous, okay, let me back up a little bit. One thing about this particular illusion is that the intersections of the lines, the yellow there, is 100% yellow, but the lines themselves are actually use transparency, so that lets some of the background darken the line and actually reduces the simultaneous contrast that you'd see otherwise. Let's see, but this is an example of an illusion called the Harman grid illusion, and the next slide is going to be another version of that optical illusion made with pure cyan. Do you see little bouncing things at the intersections of the lines as well if you look at it? That if you try and look at any particular intersection, it fades away, but you can see out of the corner of your eyes that other intersections have a little bit of a cyan image. This is basically because we have photoreceptors in our eyes that are activated by both light and dark, light or darkness, and those are basically throughout our retina. And when light falls on both types, then they cause competition between the ones that fire, and basically you get conal fatigue from this. And you start seeing things that aren't really there, like after images. So let's give our eyes a bit of a rest and talk a little bit more about Edward Tufte's indicators for ways to use color. Edward Tufte being the person who wrote the visual, I forgot the name of his book, but the visual presentation of quantitative data, very famous book. And the first of these, he actually gives 4 indicators for how color might be used for data. The first one is to label something, and when you're doing it, an example of that would be the colors in a pie chart. You'd use different colors to label the different segments of the pie chart. The next one would be if you're measuring something, and to measure, an example of this would be, if you remember, and this is going to be relevant for the next year, is if you remember those red-blue maps of political parties and which way states are leaning. That'd be an example of using color to as quantity, to indicate quantity. Third one would be to represent or imitate reality, colors representation, and the example for that would be basically photographs. And lastly, to enliven or decorate colors beauty, you can basically use anything, whatever works, in order to for that. So let's start off with the first one, to label, and I'm going to suggest using index color for that. The reason for that is that to be most effective with color, you need to basically limit yourself to as few colors as possible rather than doing a whole riot of color. And one way to do that is to limit your palette. The other nice thing about index color is that it adds a little bit of indirection between the color you're specifying and the color that's actually used to represent. So you can say color 1 and not have to worry about its RGB values. Let's see. Index colors these days are mainly used in conjunction with image data that originated from GIFs. But I don't know. I think if you are gung-ho about using hex values for your colors, then index colors might be the color space for you. And you can use other color spaces as a basis for index colors for basically everything except for pattern, and that includes separation and device N. I'm not sure that I see the point of using separation as a basis for an index color, but device N could be interesting. Okay, the next one for color as quantity, the one I like using for that would be separation color space. And the reason I like it for representing is basically you can go from something that has 3 or 4 color components to something that has just one, which is basically the amount of the percentage from 0 to 100 of how much of a tint that you're going to use for that. Makes it easier than trying to coordinate 3 or 4 different color components to get the right quantification. But let's talk about the more traditional uses of separations, which is spot colors first. Spot color is usually a pre-canned color that you put into the graphic press that is basically outside of the scope of your process colors. You can't necessarily reproduce the exact color with process colors. You might turn to a spot color to get the exact shade of red or whatever for that. But you can also use a separation color space for named colors, and those don't necessarily have to be colors per se. For example, you could use separation color space for indicating varnishing, where you actually add a clear coat of varnish to certain parts of a page in order to protect the ink underneath. Another use would be as if you're cutting the page and you want to indicate which areas of the page to cut off in a press. Die cutting would be another way to use this separation color space. And then, sort of alluded to this, spot colors can be printed as solids or halftone inks. Okay, ignoring what I said about using separation spaces for spot colors, here I'm using separation space to, I'm actually playing with separation space with an actual shading pattern. Well, yeah. To basically go from 0 at the center to 100% of the ink at the edge. Sort of as a start to doing the next slide, where I basically took an image and got separation bit mask for it and then applied the separation color space to each of the images so that it looks as if a way of basically doing a very rough, soft proof of which inks are going to be used for doing the image. All right. Let's see. So I'm also going to do a couple optical illusions using separation color spaces. Here you have two rows of diamonds, two complete rows of diamonds on the bottom and the top. Which one is darker? They're actually created the same way, but it looks as if when you look at them, the bottom is surrounded by darker, which makes the bottom look lighter than it is, and then when you get to this top, it's more surrounded. Well, one thing about this is I'm using device CMYKO to specify the color inside the separation space. It goes from basically white, 0, and to 100% magenta. Use another version of that illusion. Basically, same thing. Are they the same color or not? Yes, they are. I created this one using device RGB as the basis of the color space. Goes from 100% green to 100% black at the bottom. Okay, and let's see. Third topic is going to be color imitation of reality. And before I get to ICC profiles, I'm going to do experiment with duckies. Basically here is I replace the color space on these duckies with the Cal RGB values from the PDF reference. But the only thing I did for each of these is I recalculated the XYZ tristimulus values so that based on the standard illuminance that I found on a wiki page. So in a very loose sense, this might be how this particular image might look at different white point values. Okay, and I'm going to basically do the same experiment, but instead of replacing the color space with Cal RGB and using different white point values, I'm going to replace the ICC profile that was being used. And the question is, are all these duckies look the same or not? Because they're all identical, basically the same as before, but I'm using different ICC profiles. There are actually a number of different profiles. I basically picked up whatever I had on my system. There's about 3 different sRGBs on here. There's one, and I think this one is another sRGB. sRGB is roughly the basically the standard for monitors that are rough. Basically corresponds to the color capabilities of monitors. But thing is, that might have been more true in the 90s when it was being developed for CRT displays than it might be these days when we use LED displays and LCD displays for our monitors. There's a couple other notable ones. I believe one of these is Adobe RGB. Per the Wikipedia webpage, Adobe RGB is an incorrect encoding of the SMTP 240M standard, I believe, but it's a very popular working color space. The one thing is it's bigger than the sRGB color space, so you kind of need, to do it correctly, you need a specialized workspace and software to see your colors beyond what your monitors can display, which is actually true for basically any wide gamut ICC profile, including the wide gamut RGB. To to put numbers on it. I think wide gamut RGB can represent up to 70% of the visible colors that we can see. The Adobe RGB, I think, is close to 52% of the visible colors, and sRGB is closer to 39%, I believe. Okay, and for working with colors, well, when you're working with ICC color space, you want to establish a working color space, and usually you use ICC profiles in pairs. You have your source profile and you have your destination profile. You generally want your source profile to represent the colors, the original colors, as accurately as possible, and you want your destination profile to represent the output, the display, what it truly is capable of. Let's see. You want to calibrate and profile your, well, calibrate, actually, let me, you want to characterize your monitors to be sure of what exactly the colors they're capable of, and you want to calibrate them. And calibrating would be basically, you make it conform to a certain standard illuminant standard to bring it into compliance with, say, D50 white point. And you want to use the best profile that you can, and the best profile for printing would be one that you created based on the output that you create, an output based on the output of your particular printer, or you want to use the profile created by the manufacturer of the printer. And lastly, for decoration, and I think I'm running out of time, okay, overprinting is one way to control how colors separated interact with each other. At one point it was a way to mimic transparency, but you have to be careful with your tonal range when you do that, because you're adding a lot of ink on top of ink. Nowadays we have transparency in PDF where you specify it, but the problem with transparency is that you have to cut it up so that to the actual colors, and if you get too complex, you end up rasterizing your document, and sometimes you lose stuff like traps. Let's see. You want to avoid mixing transparency and premix spot colors because basically they don't mix well. You don't necessarily have what you anticipate. Let's move on to some illustrations. Do the lines look, a couple of illustrations based on transparency, do the lines look wavy at the edges? If it is, it's because of transparency, because the lines are actually in fact straight, but I think using about 70% opacity here. This doesn't use transparency, but the next one will, and it's basically the same illusion, but using, do the lines look straight, or do they look distorted? And is it because of it was the circles, or is it because of the color? And here I'm not using circles, I'm using transparency for the intersections of, and in my opinion, it's looking distorted, even though it's not. Lastly, patterns. I used patterns for doing the separation color wheels, and I used it for doing the shades of gray, but you can also use it for tiling. You can use it one-dimensionally or two-dimensionally. You might want to actually put your cell content into an X object so that you can use affine transformations to create all sorts of symmetry. Moving ahead of myself and moving on. If you're interested in using patterns, there's a book by Ginny Bayer called Designing Tessellations, which might be of interest to you. this is an example of using a pattern. It's not actually a tessellation because there are gaps in between things, but here it is using pattern within a pattern and moving on to this octograph using color as a pattern. And basically, to wrap things up, your eyes will deceive you, and as Albert said, and I quoted earlier, in order to use color effectively, it is necessary to recognize that color deceives continually. If your color fidelity is important to your application, you don't want to just rely on your eyeballs and the ambient light. You want to use tools to supplement that: color emitters, spectrometers, standard illuminants conforming to standard lighting, and color neutral environment, because colors around you will affect how you perceive color. And that talked about using index color space as a label, separation color space for color's quantity, ICCBased profiles to represent reality, and color as decoration, use whatever. Thank you very much. Any questions that I can answer? Nope. Yes?
I have a question about file size. If we add colors to, let's say, black and white document, how much would it increase the resulting file size?
If you're talking about within a color image, well, if you're talking about a black and white image versus a color image, a bitmap image embedded in a PDF, it'll depend on the compression, but if you look at it uncompressed, black and white image is only going to use 1 bit, and then you have all sorts of compressions for that, so it can be very significantly smaller. Whereas when you have a full color image, if it's an RGB image, you might be using 8 bits per component and 3 components, so 24 bits to represent 1 single pixel. But it's not necessarily linear to the file size because, again, you're going to have compression. But in general, color images will be significantly larger than black and white images.
How good is compression usually? How much?
It depends on how much lossiness you're willing to accept, and if you want, and what type of compression you're using. And you get pretty good compression using JPEG compression. You're supposed to get more with JPEG 2000 compression, although I have mixed results with JPEG 2000 results. But I think you can easily compress from the uncompressed version, where it's width and height times 24 bits per color. If you look at the uncompressed versus compressed, I think you can easily get 90%, and if you're willing to accept less than this, you can increase it more to the 95%. But most people aren't actually comparing uncompressed to compressed, or comparing compressed to compressed. And it's not, you can't really predict how much more compression you will have. It really depends on how busy the image and how many parts going in and out, what changes in the image you're going to see.
I'm kind of new to the colors. So does it matter if I use 1 color or 3 colors in my document?
Well,
make a difference?
if you're using 1 or 3 colors, then it should compress fairly easily. If it's more like you have a very busy image or a very high, if you have a 1 megapixel image versus a 15 megapixel image, and it's very busy, then it's going to be a larger image than if you have something that's a screenshot with relatively few colors, and that sort of, and a limited DPI in comparison. Okay. Any other questions? Okay, well, thank you.
Thanks very much.
Mm-hmm.